Hello, class. This is Mr. Hart. And in this podcast, we want to continue our discussion on sound, and specifically we want to talk about standing waves and harmonics. Now, this is one of my favorite lessons with sound because I'm personally a musician, and standing waves and harmonics have a lot to do with music, okay? Specifically instruments. They depend a lot on being able to have harmonics and standing waves that occur, okay? But before we get into that, let's first review an idea that we've talked about a little bit already with interference, okay? And this was the idea of superposition, okay? Now, it's a big fancy word, but all it means is that if we have a wave and a second wave that it interferes with, then the resulting wave is just the sum of those two waves. Now, if those waves are perfectly in phase and have the same wavelength, they'll just be the same wave but just much larger. But we can also get weird things that occur where they're slightly offset, they're not quite the same wavelength, and we get these more complex waves that occur. But this is the key idea. Every single complex wave can be described in some way as a sum of simpler waves. Okay? So even the sound of my voice, me talking, making, tonal sounds and words and things like that, it may sound like a very complex process, but somehow it's just this combination of simpler waves that makes these more complex waves. Okay? So that's what we call superposition. But let's get into why this is useful and how it relates to standing waves. Okay? So a standing wave is a wave that oscillates but stays in the same location. Now that may sound really weird because waves have to move, right? They have to travel pretty fast. So how do we get a wave that stays in the same spot? Okay. Well, that's going to come into superposition. Okay. We'll get to that in a second, but let's define some other terms. We also have what we call the fundamental frequency, which is the lowest possible frequency you can have for a standing wave. And then we have what we call harmonics, which are other possible frequencies for a standing wave configuration. Okay, so let's go to this again. Standing wave, a wave that oscillates in the same place. Now that may sound quite bizarre, okay, but it's really not too complex, okay. Basically, all you have to do is you fix the ends of a wave, okay, and because you fix the ends, that means any wave that propagates through will reflect, okay. So you can see here, I have some points of interest on this wave, okay. And if I could get the video playing, you would see that the wave would actually move up and down. But if this point and this point are fixed, when this wave propagates, when it gets to that point, it will just reflect and go back the other way. And then it will hit there and reflect and go back the other way. So because you fix the ends, you get this reflection that keeps going back and forth and back and forth. And because a wave is just the addition of all those waves that interact, you can get a standing wave, or basically a wave that looks like it just moves up and down in the same spot. So this part of the wave would just move up and down and up and down. This part of the wave would move up and down and up and down. And then these 3 points in the center wouldn't move at all. They would just stay there because of all of the interference that is occurring. Okay? So that's a standing wave. You've probably made one without even thinking about it, okay, in many cases. Think of like a jump rope, okay? That would be an example of a standing wave, okay? Playing a string on a guitar is an example of a very complex standing wave, okay? Things that have fixed ends have standing wave configurations. So if you do it right, you can do this with any sound wave, or any wave at all, actually. So this is an example of in a pool. There's a video I found where they actually make standing waves in the pool, which is pretty cool. You can see just the water go up and down, right? Just in the water, staying in the same spot, okay? And you can get standing waves. You also can see this with what are called Rubens tubes, okay? I recommend looking these up online. Basically, you just get some gas and light it on fire inside this pressurized tube, and then if you play certain sound waves through the tube, you can actually get standing waves in the flames of the tube, which is pretty cool. But same idea, you just play the right sound, it reflects in the right way, you can get this wave that doesn't move, it just stands, or looks like it's standing in the same spot because of the interference. Okay. Veritasium actually interviewed a group of, I think they were Swedish or Norwegian students. I can't quite remember. But they made a Rubens tube that was two-dimensional, so you can actually get two-dimensional standing waves where they look like they're standing in the same spot and the flames go in and out, and it's really cool looking. I recommend looking this one up online as well. Okay, so standing waves are pretty cool. It just makes the wave look like it's sitting in the same spot, but reality is just a very complex interactions of regular waves. Okay, so let's get into why this matters to music. Okay, so let's say you're playing a guitar string. Okay, now you fix the two ends of the string and you pull up on the string. Okay, very standard procedure for playing a guitar, right? So there's actually many possibilities of what can happen. You could just get the whole string to move up and down and up and down and up and down together. Okay, this is what we call the fundamental frequency, where the whole string would just want to act like one big wave together. You could also get a second harmonic, is what we call it, or basically two nodes of the wave that want to occur inside that space. So one side goes up, the other goes down, and they would move like this on the string. Okay? You can also get the third harmonic, where you get three moving up and down together. And again, you can't have anything else in between, because otherwise the wave would have to go past the endpoints, which doesn't make any sense, right? If you had like a 2.5 size wave, it would just hit at the wrong spot and it can't exist. So there's only certain harmonics, as we say, that can exist on this string. Now here's the cool part. Because of superposition, this means the guitar string is actually doing all of the harmonics at the same time. Now this one's the most prominent, and then this one's a little less prominent, and then this one's a little less prominent, but all those harmonics exist at the same time on the guitar string, which is really cool. Okay, so if we want to know what frequencies we're going to get, we can calculate these harmonics. Okay, and this is how we do it. Okay, it's a very simple ratio or relation. All we need to do is, if we want to know the harmonic frequency of, the number of the harmonic we want. Okay, so let's say I want to know what frequency the fourth harmonic will be at. All I got to do is times that number by the fundamental frequency, or f of 1 is as we say it. Okay, you could also call it the first harmonic if you want. Okay, this is the fundamental frequency. Okay, so if I know the fundamental frequency of the guitar string, for example, is 200 hertz, then I know the second frequency will be at 400 hertz. Okay, the second harmonic will be at 400 hertz. The third harmonic will be at 600 hertz. The fourth harmonic will be at 800 hertz, and so on and so forth. Okay, so all you got to do is just times the harmonic number that you want by the fundamental frequency. Okay, which makes sense because there's only integer number of harmonics you can have. Okay, so let's just do a quick example. We just talked about this. Okay, so if you have a standing fundamental frequency of 200 hertz, the frequency of the fourth harmonic is 800, because you have 4 times 200 would give you 800 hertz. Okay. You could also go backwards. If you know the third harmonic frequency is 450 hertz and you want to know what the fourth harmonic is, well, you would just need to figure out the fundamental first. The fundamental would be the third harmonic divided by 3, okay, which would give us 150 hertz. And then we'd need to times that by 4, which would give us 600 hertz. Okay, so we got to think of everything in terms of the fundamental. If you're not given the fundamental, divide to get the fundamental, and then you can figure out the problem. Okay, but this is going to be the big idea for all the music stuff we're going to talk about in just a second, is understanding the fundamental frequency. Okay, so let's get into music. Okay, specifically instruments. So for any instrument, the reason you can make different notes and the reason why every instrument sounds different is because of harmonics. Okay, instruments are characterized by their harmonic structure. Okay, so for example, I play French horn. Okay, my friend Jacob plays trumpet. Now, both me and him can hit the middle C note on my French horn and his trumpet, okay, concert C. But even if I'm playing the same note as him, we sound like different instruments. He sounds like a trumpet, I sound like a French horn. And the other person sounds like a flute, and the other person sounds like a clarinet, and the other person sounds like a violin. Okay? We're all playing the exact same note. So how is that possible if we're sending a note with the same frequency? Okay? Well, the reality is we're not just sending that note, we're sending a harmonic structure with it. We're sending other notes that are hidden underneath that go with that sound. Okay? So for example, your tuning fork is a very pure sound. It will have just the sound of the frequency you want, just the fundamental, the first harmonic. Okay? But a clarinet will have a lot of the first harmonic, some of the third harmonic, some of the second harmonic. The violin will have a lot of the first and second, but only some of the third, and a little bit of the fourth and the fifth. Okay? So based on what amount of harmonic you get determines why the instrument sounds different from others. So if I'm playing French horn and my friend's playing trumpet, the reason why they sound slightly different is because the trumpet sends different harmonics or different amounts of harmonics than my instrument does. Okay? Let me see if I can demonstrate this a little bit. Okay? So I have here a little program. Okay? This is a Fourier Analysis called iSpectrum that does harmonic analysis. Now right now there's just a bunch of ambient noise that's going off, and so it's behaving really strangely. Okay? But I'm just going to sing a note. Okay? And when I sing that note, you'll see a peak start to appear. Okay? Okay, so you saw peaks over here. But that's not the only peak you saw, right? You saw my harmonic structure with it. There were multiple peaks along with that sound that came up. Those would be the harmonics of me singing. Okay? Now, if I had a tuning fork and I just played a tuning fork, you would just see a very strong peak of the tuning fork sound. If I played a French horn, you'd also see peaks, but they'd be in different spots and different heights than me singing. So the reason why me singing and me playing the French horn at the same note doesn't sound the same is because we have different harmonic structures. Okay? Now I'm going to go up and down, and you'll see the peaks shift left and right. Okay? So these are really low frequencies. Up here is much higher frequencies. So if I start with a really low note, okay? You saw the peaks move left to right, left to right, because my voice went from low to high. Okay, so this is our harmonic analyzer, or Fourier Analysis is what it's called. Okay, but it just looks at what frequencies are present in the sound, and this determines why your voice sounds different from other people's voices, why instruments sound different from other people's instruments, even though you're singing the same sound or singing the same note, right? You're sending other frequencies with it, which is why everything sounds different, which is really cool. Okay, so it comes from harmonics. Okay, so last thing, actually two more things. One thing I want you to understand is that instruments aren't actually playing their first harmonic, especially like trumpets and wind instruments, because they don't have a fixed end like a guitar does. So if you think about, you play a note, you can consider your mouth and that mouthpiece to be a fixed end, but the other side is not a fixed end. So you can't actually hit the fundamental frequency. You can only hit the second harmonic in reality, okay? Because you need it to go up and down once by the time it goes through all of the instrument, okay? So you'll often hear them talk about the pedal tone is the lowest note your instrument can make, okay? That's really the second harmonic, okay? The first harmonic, or the fundamental frequency, is not usually playable on most wind instruments. Okay, so for example, if you're playing the second harmonic, the pedal tone at 261.1 hertz, what would the frequency of the third harmonic be? Well, you'd actually have to find the first harmonic, which your trumpet actually can't play. Okay, it would just be that number divided by 2, and you times that by 3. Okay. And you would get that the third harmonic is 391.5 hertz. Okay, if I remember correctly, that is around middle G. Anyways, the point is, right, like if you ever played the trumpet, you know you can hit certain notes on the trumpet, right? They're called partials. Those come from what the harmonics are of the pedal tone, or sorry, of the fundamental frequency. And that's determined by the pedal tone and the harmonics from that. Okay. So anyways, I wish I could talk about this all day. I wish we could go more into, the structure of music and that type of stuff. There's a lot of physics built into that. But hopefully you understand a little bit more of how the harmonics have been built into that. Okay. The last thing I want to talk about is video game music and synthesizers. Okay. There's a lot of stuff nowadays that's based on what's called MIDI. Okay, you may have heard it. It's a digital sound making system that is used a lot for like movies and synthesizers and video games, a lot of digital music. Okay, and how it works is instead of just saying, oh, my sound is at this frequency, I'm going to play that note, and my sound's at this frequency, I'm going to play that note. That doesn't sound very good. If you've ever played like old 8-bit Mario games and stuff like that, Super Nintendo, the music sounds very, computerish, right? It sounds very techno because it just is making those pure sounds. But why MIDI and other of these programs have taken off is because they've started to model harmonics better. Okay, so you want to play a note that's 200. Let's say this is 440 hertz. That's middle A. You used to just play that note, but now what they're doing is saying, oh, let's put some harmonic structure to this note. So now we're playing the 440 hertz, and it's other harmonics that are there, and we'll play on on both sides. And so they match these frequencies much better. They get the peaks. They include the note as well, but they're starting to realize and be able to model properly the harmonic structures of lots of instruments. Okay, so nowadays, if you listen to a video game soundtrack or something like that, you may not be listening to a live orchestra. You may just be listening to synthesized instruments that have been modeled very well in the computer based on the harmonics of those instruments. Okay. One of the soundtracks I really enjoyed as a kid was Legend of Zelda: Twilight Princess. Very well orchestrated, very well done. It's completely synthesized though. It's all robotic or computer sounds because they were just so good at modeling the harmonic structures of those instruments. Okay. Nowadays you've seen them kind of move back to live orchestras. It's kind of a weird trend, but anyways, the point is if you can match the harmonics, you can pretend to be that instrument. Okay, which is pretty cool. Anyways, I hope you've got a little bit more appreciation for music and how it is connected to physics. I hope you understand how standing waves are related to harmonics and how harmonics determine how everything sounds different. But go ahead and do the homework. Hopefully this all made sense. Let me know if you have any questions, and thank you for watching.